Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be exploring RC circuits a little bit more um, via some of the graphs that, um, let's say, are associated with them. You could think of these as being, if I were to hook up the RC circuit to an oscilloscope and look only at the trace of what the circuit was making, and of course, it's an ideal circuit, ideal oscilloscope, that kind of thing. But we want to look at a little bit of how to interpret these graphs, in part because I think that this is a very important skill to have, and you really should, in a good physics class, get a little bit of discussion of graphs. And I don't really think that that discussion should be limited only to labs. So RC circuits are one area that I typically like to introduce graphing, and not really introduce it, but kind of like interpretation of graphs and how the different parameters can affect the graphs and that kind of thing. So let's look a little bit at that today. Now I've basically written some code in new Octave to simulate the behavior of the RC circuit as far as things like voltage and charge and current and that kind of thing. Why new Octave? Well, when I wrote this code, I was working predominantly at Troy University. They didn't want to spend money for MATLAB, especially if it wasn't going to be used to bring in a lot of money for research purposes. And at the time, I didn't really see that as something that I needed to do. I didn't really want to convince them to buy MATLAB for me when I was predominantly planning to use it for teaching purposes. It is a very powerful tool. Octave is a free version that kind of mimics it. And so the second reason why Octave is you can sort of make this code yourself at home if you were so inclined. That said, at the university that I'm at right now, it turns out that they have a site license for MATLAB because they have an engineering program and they have enough people here who use it, myself included, that I could do this on MATLAB. Ironically enough, they don't allow Octave on their computers here. So just a little historical aside for you. This code is very straightforward and simple. Essentially, what I do is I set up a circuit. I have an EMF, which I'm labeling as E. I have a resistor value. I have a capacitor value. And then essentially I sort of like set up an interval of time over which to watch each part of the circuit. So essentially I can look at what is the capacitor doing and what is the resistor doing. Now again, this is a simple code. I'm not doing anything fancy like, or even not really fancy, just nothing complex beyond a simple it's charging or it's discharging. You know, the obvious extension to this would be, so what if we added a square wave to it, or what if we applied a sine wave to it, or something like that. I'm not trying to do any of that here. And for an algebra-based course, that might be, you know, square wave would be fine, sine wave fine. We discuss that later. Something like a triangle wave may be a bit much, but if any of you watching this are up for the challenge, you can. Then I have a little bit of code here for essentially what type do I want. And so if the capacitor is charging through the battery, then it's type 0. If it's discharging, then it's type 1. And essentially you need to tell it that it's either type 0 or type 1, and that's this line right here. Do you want it to charge or to discharge? And then the rest of the code in here is basically just calculating for each of these two types what the charge on the capacitor is doing, what the current through the resistor is doing, what the potential energy stored by the capacitor is doing, what the power dissipated by the resistor is doing, and what the voltage drops for the resistor and the capacitor are doing. And then I have those in essentially MKS units, and then I have them also in CGS units, or quasi-CGS units, since these are millijoules and milliwatts. But I have millicoulombs, milliamp, millijoule, milliwatt. So then the next part of the code is just telling it to plot all these things that it's calculated, and there are up to 6 plots that can be generated. So right now it's set up as a type 0, and I can run, and essentially it generates these figures for me. And the figures fill up more space than the recording on my screen share. But figure number 1 is basically your voltage drop for the capacitor. Figure 2 is charge on the capacitor. You'll notice that these two graphs look very similar. They are very similar. They're both of the form. So we're charging. So we're looking at graphs that have the general form that the voltage drop V sub C, or delta V sub C, is epsilon, that's E in the code, or capital E in the code, times 1 minus the exponential e to the negative t over tau, where we expect tau is RC, and the little e is the natural number, so that's 2.781828 ... Okay, and then remember that Q is C delta V, and so we would expect for Q to look like C times epsilon times 1 minus e to the negative t over tau. So fundamentally, this right here is your portion that is a function of time, and since it's the same for both, then I get for figure 1 a graph like this, and I get for figure 2 a graph like this. There's the same kind of graph. And so I'll just put the two on here, although they seem to have copied weird. They kind of scrunched up a little bit. All right, that's a little bit better. So I'm not actually going to go too much into the figuring out the parameters from the graphs on this video, by the way. This is kind of going to be a two-parter. This one, we're just looking at the general shape, and we're looking at what happens if I make a simple change. So, it turns out that epsilon is this asymptote, Q max is this asymptote, that kind of thing. But these both have the shape that delta V as a function of time is proportional to 1 minus e to the negative t over tau. And Q as a function of time is proportional to 1 minus e to the negative t over tau. We could say essentially Q of t is Q naught, or Q max, times 1 minus e to the negative t over tau, for example. And then we can also look at the other graphs. So this one right here is voltage across the resistor as a function of time. And you'll notice that it's a more obvious exponential decay. It turns out all three that I've shown so far are actually exponential decays. It's just that these are decaying up from 0 to some value, whereas this one right here is decaying down from some value to 0. And in fact, that value is 10 volts. If you look at this one, it's approaching 10 volts. And if you look in the original code, my EMF is 10 volts. Okay, so we're getting a little bit of the parameters out of this by necessity. Why does this one do this? Because recall that our loop rule says delta VC plus delta VR minus epsilon is 0. And so that means that delta VR, which is what's being plotted over here, this is delta VR, must be epsilon minus delta VC. But recall that delta VC is itself epsilon times 1 minus e to the negative t over tau. Okay, so if you combine all of that, you get that delta VR in this case is just epsilon e to the negative t over tau. All right, let's look at another graph. So this right here is your magnitude of your current as a function of time. And this one right here, if we copy it over, put it in here so I can write on it. Why is this one of this shape? Well, because Ohm's law is basically telling me that delta V sub R is I times R. This axis right here would be I. But that just means that I is delta VR over R, and we just established that delta VR is e to the negative t over tau. So you're looking at epsilon over R e to the negative t over tau. This also means that if I put the two side by side again, as I did with the charge and with the voltage for the capacitor, that I expect them to have a similar shape, and lo and behold, they have a similar shape. They both have a proportionality to e to the negative t over tau. I'm not going to do the power graph, but I'll do for stored energy, which is this one right here. How do you get stored energy? So this one's different than the other two for the capacitor. So the capacitor, again, that is actually storing energy. And this one is, it looks kind of sort of like these two, but it's not really. And the reason why it's not really is because for a capacitor, U should look like 1/2 Q delta VC, which is the same as 1/2 of Q squared over C, or 1/2 of C delta VC squared. So this graph right here is what you get if you multiply this graph by this graph, or if you were to square this graph or square this graph and multiply by an appropriate constant. That gives us an equation, by the way, that looks like this if we're using 1/2 C delta V squared. Now, I'm going to do a couple more things on this video. One of them is that I want to change from the charging to the discharging. Essentially, that involves changing this this type right here from 0 to 1. We want a discharging graph. So I'm going to hit the record button again, or the run button again, and then we can look through each of these graphs and see what's different and what's the same. All right, so if we go back through these graphs again, here's the voltage drop across the capacitor as a function of time. So before, that graph looked like this. Now that graph basically looks like this. It's an exponential decay. It's an exponential decay from a value of 10 to a value of, it's basically asymptotic to 0. And likewise, if I look at figure 2, which is the charge stored by the capacitor, I end up with a graph that's now looking also like an exponential decay. Well, this is because you'll recall that for discharging, delta VC is basically delta V naught, the initial potential across your capacitor, times e to the negative t over tau. And that also implies that Q as a function of time, this is delta V as a function of time, Q as a function of time must be delta V naught times C times e to the negative t over tau. And this term you could also refer to as Q naught. So it's now an exponential decay back to 0. Well, the circuit for discharging, if you recall, basically has a capacitor and then a resistor in it, which are in series with each other. So I have a delta VC and I have a delta VR. And so this implies for discharging that delta VC is equal to negative of delta VR. And that negative sign mathematically maybe matters, but if you were trying to measure this with an oscilloscope, you could simultaneously measure both the resistor and the capacitor, and all that you'd find is you just need to flip the leads around on the resistor relative to the capacitor, and you'd end up getting essentially the same signal. So if we go and look at what the resistor is doing, here is the voltage across the resistor, and it's actually pretty much an identical graph to what we had before and to what we have with the capacitor. And then this right here is the current as a function of time for the resistor. Again, it's identical to the graph we had before. So if I come back in here, I could do a couple side-by-sides. One of them would be before and after with the resistor. The other could be the resistors versus the capacitor. Either way, you're going to find that they look pretty similar. So here's the resistor as a function of time, and then here is the current through the resistor as a function of time. And so you've got exponential decays in both cases. If you were to do a side-by-side of these two, so let's do the resistor voltage drop, and let's do the capacitor voltage drop side by side for this discharging case. And lo and behold, the two graphs are identical to each other. So this is for capacitor discharging through resistor. And they are, again, identical to each other for this simple circuit because of the loop rule. So you have, again, presumably a circuit looking like this. Now, it would look different if you had, for example, a capacitor and then two resistors in series and you measured across one of the two. It would also look different if you had the case where your capacitor is discharging through a resistor and a battery with some EMF. Essentially, you can charge the capacitor up to a value with say a high voltage source, and then somebody comes along and accidentally hits the knob on the voltage source, such that it drops from, let's say, 12 volts to 5 volts or whatever. Well, the capacitor will start discharging through it, but you still have that 5-volt EMF at play. We're not really trying to deal with either of those things in this video or lecture. Okay, what about the side-by-side of capacitor charging versus discharging. So if we come back up here and just grab the voltage for the charging capacitor, that could go right here. And now let's grab the discharging capacitor. Whoops, that would be this one right here. So let's throw that one in. And here they are side by side. We can label them. In some sense, this is equivalent to having, by the way, a circuit like this that has a switch that you can switch to point 1 to charge it or switch over to point 2 to discharge it. It's also kind of the, if I applied a square wave from a power supply, then when the voltage is on, I get this, and when the voltage is off, I get this. So those are different ways of looking at that. There's really one other thing that I wanted to do in this video, which is kind of like look at what the effects are of changing some of these parameters. And that can take a little bit of time as well. This is, of course, a bit longer of a video just because of the nature of it and, 2 parts and all that. And we can look at both the charging and the discharging case with parameter changes, but that would take a bit of time. So I'm going to do kind of a sample by way of coming in here. Let's leave it as a discharging for the fun of it. Let's see what happens if we change the value of R from 2,000 to, let's say, 1,000. So if I rerun this, I get a bunch of new graphs again, and they look pretty similar. For example, this right here is my voltage drop across the capacitor versus time. And if I put it side by side with the old voltage drop across the capacitor versus time, here's my sort of old voltage drop. And the graphs themselves look at a glance similar, but if you look at the time axis, so the y-axis, everything's the same, shape basically the same. If you look at the time axis, this one right here was with R is equal to 2,000 ohms. This one right here was R is equal to 1,000 ohms. And you'll notice that the time axis has changed in as much as these numbers are all half as much as these numbers, or the numbers here are twice as much as the numbers here. So doubling the value of R or having the value of R causes a doubling or a halving of the discharge rate in some way. So let's go back and let's change the value back to 2,000 as we had before, and let's change the capacitance now. Maybe instead of to 0.05, maybe we'll make it or 0.0005. We can make it 0.0010. So I've basically doubled my capacitance. And again, remember that I've returned my resistance to its original value. So let's look at what we have here. Again, we'll look at figure number 1, and let's go ahead and copy that one. Let's put it down here. And let's take this one, which was the original, and put it here so you've got a side-by-side. And again, they look similar, but again, notice what happens with the time values. So this one was C is equal to 0.0005 farads. This one was C is equal to 0.001 farads. And in both cases, R is 2,000 ohms. And in both cases, EMF was 10 volts, or initial voltage. So EMF doubles in my code for that. So this right here is really just delta V naught. And so again, doubling C seems to double the amount of time over which the discharge is happening. It kind of like slows the rate of discharge by a factor of 2, and therefore sort of like doubles the amount of time taken to get to a given voltage. All right, and let's change also the discharge or the EMF, the initial voltage in my code. So that basically involves going back through here, resetting this, and let's make the EMF, let's say 20 instead of 10, and we'll run it again. And again, here's what I end up getting. So copy this one, come down here, and this is with doubling my sort of initial voltage. And it's kind of got a little crowded here because of the way I set up my scales, but essentially the shape is the same. I'm starting from 20 rather than from 10, and I'm finding that, let's say, to get from 10 down to 5, which is half, here's 5, I come down here, I'm kind of like roughly midway between 0.6 and 0.8 seconds. From 20 down to 10, with this crowding out, that's a little rough. So pull open the figure and make it a little bigger, maybe. So here's 10, and I kind of drop down, and I find again I'm kind of midway between 0.6 and 0.8. So somehow the discharge rate as defined by time it takes to get from a given value to fraction of the given value remains the same. If you were to measure essentially like how tall is this line, if these two are the same height of graph, how tall is this line versus coming over here and measuring how tall is the same line over here, you'd find that they're about the same height. And essentially that means that my rate of halving is the same. It's just that how much voltage is half is twice as much for this one as for this one. So that's basically what changing those parameters do. We can also, for the fun of it, just go back and let's reset this to 10 so that axis isn't so crowded. And then let's change the type over to type 0 so that we're charging. And here's my voltage drop versus time for that. And once again, let's have the value of R and run again and copy this one over. And just as with the other discharging, doubling R seems to double the rate.